also this one. So for questions, I will give them the mic. There's only one, and then you can answer here. Just have to press here. I can do it also. What time is it now? I know this. I think we can start. So there is no break between the lecture and tutorial, but if you need 1 minute to relax.
Yeah, I might probably take like
just take some water or something like this. Because I know speaking 1.5 hours is a lot. Okay, good morning, everyone. Welcome to the last day of the school. So our first lecture today is from Robert Pinsler from Microsoft. And yeah, Robert, you can start.
Thank you. Yeah, good morning, everyone. How are you feeling on the last day? Bit tired, maybe? Yeah. I heard you had a nice dinner yesterday. That went well? Nice. Great. Yeah, sorry for the early time. I know it's a bit rough for some. I don't blame you if you take a little nap in the meantime. But yeah, let's get started slowly. So yeah, my name is Robert Pinsler. I'm from Microsoft Research. And today I'm going to talk a little bit about generative models for molecules and materials. I confess I've been a little bit sick before, so I couldn't maybe prepare the way I wanted. So it's mostly going to be generative models for materials, to be honest. But I will still try to molecules a little bit as well. So let's get started. As I'm sure you're all aware, both molecule or both sort of drug design and material design are incredibly important for society, right? Like if you just look at materials design, it's used in so many different applications like batteries, solar cells, carbon capture technologies. Maybe what's very relevant for Microsoft is also you need a lot of materials to build data centers. And so obviously one problem is sort of designing new material, bringing them to market takes an incredible amount of time and can be incredibly expensive. And there's this overused sort of analogy of trying to find a needle in the haystack, but it is really hard to find a new material that has sort of really good properties for the applications that we need. So obviously we want to do better than that, and we don't rely sort of on human intuition and luck and all of these things. So the main question really usually is, how can we find molecules and materials that have properties that satisfy certain design requirements? And so we can think of this as sort of a forward and an inverse problem. And so in the forward problem, we have some drug or material candidate, and we're just trying to measure its properties or predict its properties. And in the inverse problem, we're trying to go from property and predict what the structure or the material would look like. And so we can use sort of machine learning for the forward and the inverse problem. And I think you've already heard quite a bit on machine learning force fields during this week, for example, from Ilias on Monday. And you use that to accelerate the simulation of properties. And then to solve the inverse problem, you could use some sort of generative models to accelerate the design of novel materials with certain properties. Okay, and so if we contrast this to sort of what you would do traditionally, then you can really see the benefit, because if you take a standard materials screening pipeline, you would maybe start with a few tens of thousands of materials. You would screen them for different properties and then send them to the lab. But first of all, this is sort of constrained by the number of known materials that you already have, and it's also cumbersome sort of to do this gradual filtering. So as I said, you're basically limited by the number of known materials, but the potential space of useful materials is much larger, and I think if you go to drug-like molecules, it's even 10 to the power of 60, something ridiculous like that. Whereas with generative models, you could imagine generating the materials directly, which is much more powerful and gives you access to a much larger space. Okay, so for the remainder of the talk, I'm roughly going to go talk about 4 different things. First of all, I'll give a little bit of an overview of what are, I think, the key ingredients for generative modeling for molecules and materials. Then I'm going to give an introduction to diffusion models, followed by a deep dive on MetaGen, which is a generative model for materials design. And then I'm going to talk a little bit about some other, some more recent generative modeling approaches. Okay, so what do we need? So to think about how do we design sort of a generative model, I think we need 4 things. First of all, we need to think about how do we represent our data. There are many different ways, and there's usually a trade-off between sort of simplicity and flexibility, right? So the simpler representation we use, the easier we generate, because you basically have a smaller design space. On the other hand, you might lose flexibility. Then you need to think about what task are you trying to solve. So we've already talked about inverse design, but there are some other tasks that you might be interested in. Then obviously the model architecture and sort of like the actual generative modeling approach. And finally, and I'm sure you've heard about this a lot during this week as well, is we might want to think about some invariances or equivariances that we want to bake. Okay, so starting with the data representation. So if we think about molecules, then we could go all the way to 1D, right? So something like a SMILES string. And if we have a model that can spit out SMILES strings, that's a generative model for SMILES. But that has some limitations, right? It's very hard to actually build valid SMILES strings and so on. So we could go to 2D and think about molecular graphs, where the nodes are the atoms and the edges are the bonds. And I think there's been a lot of work on that as well. And if we could go all the way to 3D, where we directly model the coordinates of the structures. And here you see a lot of different parameterizations that you could think about. So, for example, you could model them directly in Cartesian coordinates. You could think about modeling or sort of picking a reference atom and then just modeling distances and angles towards that reference. If you think about metals, you could work in fractional coordinates, and then you have the periodic lattice which together sort of describe the entire crystal. You could work something like Wyckoff representation, and if, for example, our representation would be a CIF file, right, which is also something we could generate, then that's basically also based on Wyckoff positions. And similarly, if you think about the lattice for crystals, represented using lengths and angles, but we could also directly represent it as essentially a 3x3 matrix. And as I'll show later, we can still reduce that to 6 degrees of freedom, similar to lengths and angles representation. So there are lots of choices here, and it's maybe not always clear what's the best, and it might depend on your model, on application, and so on. Okay, so the next is the task. So the most basic task we could think about is actually unconditional generation. So we just want to generate a structure X by sampling from a distribution or a learned distribution P of X. And actually not a very useful task in practice because, generally speaking, we're not interested in generating randoms or sort of unconditional structures with random properties. But obviously useful if you want to develop a new generative model. It's a much easier task. And so even that we can sort of differentiate between structure prediction, where you're given the atomic numbers and you're just trying to predict the positions and the lattice. And you have de novo generation, would jointly generate everything. So usually that's sort of how it's differentiated. And then you have the conditional generation task, and here really the could be almost anything, right? So it could be several conditions or several design requirements, such as here on the right. You see this solid electrolyte of a battery material, and you have all these different design requirements that you want to satisfy, and you could all encode those into the condition. Y could also be another structure. It could be something like a band structure, XRD spectrum, and so on. So yeah, it can really be very flexible. Then the third part is obviously the model architecture. So what sort of generative model do we want to use? So I guess historically, there's been a lot of work on variational autoencoders and GANs, also flow-based models, and obviously since maybe 2020 or so, it's been at least the structure-based generation has been dominated by diffusions, and also more recently flow matching. And then on top of that, you also have generally autoregressive models. For example, if you have a LLM to generate text, then that would also fall under that category. Okay, so just to remind yourself, so a GAN, obviously, you basically have this generator that tries to generate structures given this representation Z, and then you have a discriminator that tries to tell whether the generated structure is sort of a fake, a generated structure, or it is actually a structure, a real structure, and that is then used in some adversarial loss to train both the generator and discriminator. Then yeah, we have the VAE. Here you basically have an autoencoder, so you're trying to encode some input into a latent Z. That it will typically be bottlenecked, and then you're decoding again to reconstruct, and you have some reconstruction loss. And what makes it the VAE is that before you decode, you're essentially sampling a latent, so you're really modeling addition over latents. And then for flow-based models, the idea is that you're basically applying a series of transformations to get from some base distribution to target distribution. And finally, for diffusion models, and we'll talk more about this later, the idea is you basically have a corruption process where you gradually apply noise until your input is completely denoised, and you learn a denoising process that lets you gradually denoise the structure and generate a clean structure. Okay, so let's look a little bit more into detail into diffusion models, which is also something we will need to understand MetaGen. So first of all, diffusion models are an example of deep generative models, and the idea, broadly speaking, is that we have some sample data distribution, and so we're going to train a neural network that helps us to model or to approximate this distribution, and then at sampling time, we can sample from this. We can easily sample from this distribution to generate new examples. So very simple, and so diffusion models specifically, as I said, they have this fixed forward corruption process, and they have a reverse denoising process. So here in this example, we have this image of a dog, and you see at the bottom it gets gradually corrupted until you basically just have white noise. And then at the top you have this reverse denoising process where at every step you're trying to essentially predict the slightly cleaner version of the image. And so later we will essentially apply the same idea to materials so that we're able to generate materials. And so obviously the idea here is we don't just want to reconstruct images, but at sampling time you could sample any random noise and then generate a potentially never seen image. Yeah, question? Oh, sorry. Okay. Right. So underlying this something called the denoising diffusion probabilistic model. And so let's unpack a little bit what's going on here. We have this transition kernel Q of xt given xt minus 1. And so that is basically just some Gaussian noise. So it's a Gaussian distribution centered at xt with some mean and variance. And you can then also run a joint distribution, which is something we will need later. And now the trick is that we can define a noise schedule of these alpha t values. And it's constructed in a way that basically alpha goes to 0 as t as we approach capital T, and capital T is basically at the point where the image is completely noisy, whereas 0 is the noisy regime. And what this allows us to do is, or what this means is two things. So first of all, Q of xt given x0 is also a Gaussian, because everything is sort of closed form, which is nice. And so what it means that given a clean image x0, we can directly go to a noisy version Q of xt for any t. We don't have to do this gradually, but we directly jump to the noisy version, which makes training a lot easier. And the other thing, what it means is that in the limit, Q of xt, or capital T given x0, will approach a Gaussian with 0 mean and unit standard deviation. And so because sort of the variance of this limit distribution is bounded, we also call it variance preserving diffusion, and another version that's called variance exploding diffusion, where the variance is basically going to infinite. And that also has its applications, but we're not going to cut today. Okay, and then we can look at the reverse denoising process. So we have the distribution over x capital T is a unit Gaussian, and then we want to model p of theta xt minus 1 given xt, right? So this is something that needs to be learnable, and we will use that to gradually denoise our image. What we have is we basically parameterize the mean of this distribution. We could also parameterize the covariance, but here we keep it fixed. And so this mu of theta will be a trainable network that takes a noisy image xt and a time step. And then we can figure out what's the joint distribution. Okay, so how do you now train this thing? Define the forward corruption process. We can easily sample arbitrary noisy images, and we've defined a parameterized reverse diffusion process. So the usual way to train sort of these kind of models would be just by looking at the variational upper bound. And so I'm not going to go to the details. But one thing to point out is that instead of predicting, or instead of sort of modeling the mean directly, we could also do a little reparameterization, which is usually practice, where what you're actually modeling or trying to predict is the noise, okay? So if you do a little bit of maths, basically you can see that xt, if you do the reparameterization trick, it becomes this sort of square root of t times x0 plus square root of 1 minus alpha t epsilon. And then you can use that because you know x0 at train, you know xt, so you can rewrite it in terms of epsilon, and you can actually directly parameterize epsilon. And so this leads us to the loss at the bottom. It's actually very simple. It's really just a squared loss between the true epsilon and the predicted epsilon and some extra terms. And then you have an expectation over, first of all, x0, which is easy to get. Then you have an expectation over time steps, which is just a uniform distribution. And you sample noise from a unit Gaussian. Okay, and then we also have this lambda parameter there, but actually it turns out in practice you usually set it to 1. So to summarize, you sample x0, you sample t, you sample an epsilon, and then you take a gradient step on the squared loss until everything is converged. And if you want to sample, all you need to do is you sample x capital T, which is easy to generate, and then you iteratively first sample a z. If your t is larger than 1, so here, suppose, goes from, sometimes you think about it sort of from 0 to 1. Here, I guess it's, capital T is something like 100 or 1,000. So as long as t is larger than 1, you're going to sample z, and otherwise you set it to 0. And then you just plug it in there at the bottom, and you'll use your learned epsilon network. Epsilon. You'll use your z, and you're gradually sort of predicting xt minus 1. And if you continue doing this, then you're gradually to an x0. Okay, so there is also another derivation, which is maybe a little bit more involved, so I'm not going to go through that today. But it's essentially equivalent, and it's based on differential equations. And so the objective you end up with is the one at the bottom. It actually turns out it's essentially equivalent to to what we just went through. The only thing I want to highlight is so the loss at the bottom is formulated in terms of this S theta, and it's essentially now a squared loss on score of the diffuse data sample. And so the score function will pop up over and over again, and it's a very useful quantity. So we can just think of sort of S theta now as approximating the score, which is just a gradient with respect to the data xt of log qt given xt of n x0. Okay. So we also said we want to do inverse design, right? We want to do conditional generation. So how do we do that, given what we've seen so far? So this is where the score view becomes handy. So first, what we really want to do is we want to model a conditional distribution P of xt given some condition y, which ultimately what we need is now a conditional score of P of xt given y. And so the first thing we can do is just apply Bayes theorem. And if we then take the log and take the gradient, one thing is that obviously the gradient of log P of y with respect to xt is 0, so that drops out, and we are left with just this, right? And this directly leads us to classifier guidance, which basically says you take your unconditional score, which you're training anyway, and all you need is essentially a classifier, right? Log of P of y given x classifier. The only sort of special thing about this classifier is that it takes noisy structures, right? xt can be noisy, so you need to train a way that it knows how to deal with noisy structures. But you can really train this separately. You could use any supervised learning sort of approach to train this, and you just plug it in here. And so it's called classifier guidance, but obviously it also works for continuous properties, right? Which is maybe something we'll see more often for molecular or materials design. Okay, but actually what people usually use in practice is something called classifier guidance. And it turns out it's also very easy to derive. So we arrived at classifier guidance by applying Bayes theorem. How to apply it again? And so if we look at this log of P of y given xt at the top, we can write this using Bayes theorem. We again take the log, we take the gradient, very similar, so the log of P of yt x out. And if we then plug this back into the classifier guidance formula and rewrite it a little bit, we arrive at the bottom. And so now what we're left with is essentially, again, this unconditional score and something that looks like this xt given y. Yeah, that's a typo. So this should be xt given y, which is a additional score, right? So the way you would train this in practice is you're just learning one score model, a conditional one that takes y, but every now and then you'll just drop out the condition and set it to some null value, and so you can either use it in a conditional or an unconditional setting, and so you can either get an unconditional or conditional score, and that's how you can evaluate this. And it's actually, if you think about the score as sort of like a vector, right? It's really just a linear interpolation of two vectors. So you have this score that points you in one direction that says, oh, to denoise the data, you should go in that direction. And the conditional score is telling you, yeah, but if you also want to satisfy the condition, you should move a little bit more in that direction. And you're just linear interpolating between the two. And another way to look at this is to say, if we actually if we would remove the gradients and go back to sort of exponentiate everything, you would actually see that this gamma and exponent, right? So really what you're doing is you're exponentiating this conditional distribution to accentuate the condition more. Okay, so with that, I want to talk a little bit about MetaGen. So MetaGen is for periodic structures, and now with this better understanding of diffusion models, I think it will actually be very easy to understand MetaGen. We literally plug in materials and have the same thing. So here in the forward corruption, we start from some stable material that we know, we corrupt it until we have essentially a random material. And then in the reverse denoising process, we're trying to recover the clean image. And so going back to what I said earlier, we need to think about what is our representation, right? So here, obviously, we have some sort of 3D representation. And obviously, crystals are sort of solids that are periodically, have a periodically repeating structure. The way that we can model this is with this lattice. And so essentially we can represent the crystal structure as just a list of atom types. We call them capital A. Then we can model the positions in terms of the fractional coordinates that are in the sort of between 0 and 1 in this three-dimensional space. And finally we have the lattice, which are just three-dimensional vectors that tell us about the periodicity, of the structure. And it's very easy to then Cartesian coordinates by just using the fractional coordinates and the lattice and doing some linear algebra. Okay. Okay, so next, what is actually our objective here? So the objective is first, in the unconditional case, we just want to generate stable materials that are periodic in 3D. And we have this distribution over atom types, atomic numbers, and a lattice. And we have some additional requirements. First of all, we want the generation process to respect the properties of 3D materials, mostly periodicity. And we want to be able to add different conditions later on. Okay, so let's look at the forward corruption process. And so the one assumption that we are making here is that the forward corruption factorizes into 3 different components. A corruption of the atom types, of the coordinates, and the lattice. So we can just treat them separately, which makes things a lot easier. So let's start with this. So atom types are obviously discrete, so that's always going to be a little bit tricky. You have the same thing for molecules. So you need to treat them differently as these quantities. And here we're using something called D3PM, which is a very popular sort of mass diffusion approach. And the idea is that corruption is basically, let's maybe go to this. Yeah. So essentially what this is saying is that step, you have a probability of beta of transiting to a so-called mass state. So if you look at this image, everything that's gray is a mass state, and over time it will just mask out all the elements to some sort of dummy atom or mass state. And conversely, you have a probability of 1 minus beta of staying unchanged, unmasked, and once you're masked, there's no going back. Okay, and there are different versions of this, but apparently mass diffusion seems to perform. Okay, so before we move on, I want to highlight one subtle sort of corruption when you have periodicity, which is if we construct a graph, right, which is something we might want to do, we sort of might want to use the graph neural network later to sort of process these structures. Then if we look at the nearest neighbors, these would be the nearest neighbors if we don't have any periodicity. But of course, we have periodic structures, so we actually have all these periodic images. So if you look at the periodic nearest neighbors, we also need to take those into consideration. And another thing that we should keep in mind, yeah, so this is just another view of what I just said. But what happens if we now add noise to this? Okay, so if we a little bit of noise to the blue atom and move it, and we happen to push it across the boundary of the unit cell, well, obviously it will there will be an image that re-enters from the other side. So we push this one out, but there will be one sort of sitting here that would now move in, right? We need to take that into consideration. And similarly, also what's important is that even if we don't change the positions directly, if we change the lattice, the absolute positions of the atoms will also change, right? So there's a dependency between the two. Okay, so with that in mind, how do we model the diffusion of the fractional coordinates? Well, we should really take periodicity into account. Right? And so the way we can do this is by using something called the wrapped normal distribution. And the idea is that we don't just take the probabilities of the sort of the non-periodic neighbors into account, but essentially it's sort of a mixture of Gaussians where we sort of add all the periodic images as well, and we are summing those up. And in theory, that would be an infinite sum over all periodic images, which obviously is intractable to compute, but fortunately, we sort of have thin tails, and so we can just truncate the sum, and it's going to be a pretty good approximation. Okay, and finally the lattice. So as I said, here we are modeling it as basically just three-dimensional vectors. If you compare to a parametrization where you just use the lengths and angles, you just have 6 degrees of freedom, whereas here you have 9. And ideally, you just 6 degrees of freedom. And so it turns out there's a way to also reduce this to 6. And the way to do this is to do a polar decomposition of this lattice matrix into a rotational matrix and a symmetric matrix. And obviously, we don't really care about the rotation, so we can throw that away and just care about part. And as it turns out, that only has 6 degrees of freedom. So what we're essentially doing is we're starting with the symmetrics, and we just keep adding symmetric noise so that we always only have 6 degrees of freedom. And another problem that is if you do just naive diffusion, then, as I said earlier, your limiting distribution would be this standard Gaussian. But one problem you have is highly skewed lattices in the limit. And what it means is that you will pack a lot of neighbors into a very tiny, so they become very dense, and it leads to all sorts of numerical issues. So ideally, we want to avoid that. And the way we avoid it is we just define a custom limit mean invariance, which is basically cubic, and we scale it by the number of atoms. And this doesn't really introduce any bias, so once fully trained, we will be able, from this limiting distribution, to then denoise to any structure we want, but numerically it's just much more stable and easier to train. So that was the forward corruption. Now we'll go to the reverse process. So, as I said earlier, essentially what we need is this score, so the gradient of the log probability. And so the input will be a structure, and the output will be this. And so now is the time to think a little bit about which symmetries we want to exploit. And so if we think about the atomic number, then we really want invariant predictions, right? We don't want the score to change just because we rotate or translate the input. For the positions and the lattice, though, our score, which is really a vector, right? It should rotate when the input rotates. And we can use an accurate to achieve that. And in this case, we use one called GemNet. And then train it, you also need some training data. And in this case, again, our objective is to directly generate stable or metastable materials across the program. So we collected a data set of around 1 million structures, and then we do a lot of deduplication and filter. One of the filters we apply is that we restrict it to 20 atoms. That was sort of the maximum we could model at that time. We only include structures whose energy is within 0.1 EV per atom above the convex hull, where the convex by this reference data set. And this then still results in around 600,000 training structures that we can use to train our model. Okay, and if you now do unconditional generation, you might get structures like this. You guys probably understand better than me if these are nice. All I can say is they look reasonably symmetric. They look reasonably diverse in terms of sort of structural and chemical composition. Do you have a question? Oh, these are also not cherry-picked, so I'm sure some of them are debatable. Okay, if we now look at sort of some quantitative metrics, one way we measure the quality of our model is at the percentage of structures that the model outputs that are stable, unique, and novel. And in the tutorial, I'll talk a little bit more about those. So just as sort of as given. And we can see if we compare Metagen with other generative models before on the same data set MP, then we see about a 1.6x improvement because of. And if we then also scale the data, we see another 1.7x improvement. And another thing that we like to look at is if you take the generated structure, you relax it, and you compare the RMSD between the generated structure and the relaxed structure, how large is RMSD? And as you can see, again, you get around 2x improvement over prior work just because of the model, further 5x improvement because of the data. And so, okay, so before I move on, I think go a little bit over time on this part and spend a little bit less time on the tutorial. But we can also take a quick break after this part. Okay, so really what we care about is conditional generation. So what we want to do now is we want to fine-tune this unconditional base model that we also can do conditional generation. So, for example, some conditions that we looked at is conditioning on chemical systems, space group, and a whole range of different properties. And the way we fine-tune the model is essentially by adding some approach called ControlNet. And the idea is essentially very simple. You encode your condition, you send it through an MLP, and you add it somewhere back into your model, and you sort of jointly fine-tune that. Okay, and now you can do conditional. And so here we condition on 3 different properties: magnetic density, band gap, and bulk modulus. And in the figures at the top, you see in gray, you see the data distribution. And in green, you see the distribution of the stable, unique, and novel samples and their properties that we generated. And you can see that we're actually able to shift the distribution quite a bit. And so band gap, you can see, is a little bit less successful. That's not surprising because for both magnetic density and bulk modulus, I think it depends much more. It's easier chemistry, right? For band gap, it depends more on structure, so it's actually a harder inverse problem. And on the bottom, you see some structures that we generated. One thing, so at the beginning we talked about screening, right? And that maybe generative models are better than screening. So let's show really the benefit. So here we see if we compare Metagen compared to screening, given a limited number of DFT budget, then we see that for screening, at least in this example, it doesn't always. Screening will at some point saturate because we essentially run out of structures that we can screen, whereas our generative model keeps going. Finally, we did some sort of toy experimental validation, I would say. And our goal was to find a novel oxide with a bulk modulus value of 200 gigapascal. Not super high, but also not super low. We started with generating 8,000 oxides generated by Metagen. We then filtered them with filter using things like energy and phonon stability. Then we applied some more quantum calculations, did some sort of expert selection, and then sent 4 of them to the lab. And in the end, what we found was this. So what the model generated with top TA-CA206, I think. And we predicted 221 gigapascal. And what we then synthesized and characterized was this. And that's essentially a disordered version of what we generated. And so you can see the XRD spectrum at the bottom, and you can see a little sample here. Okay, so let me maybe wrap up with this part, and we can take a quick break and jump to the tutorial. So I want to talk a little bit about some modeling approaches, some of them more recent. And actually, this one is not so recent, and it's also it's close to my heart because I think it's the first AF for Science paper that I wrote. So I quite like it. I just want to show a little bit of variety of things you could do, right? So far we just talked about supervised learning, but this is actually an approach where you use reinforcement learning to design molecules. And here the idea is we have this, back then we called it a bag of elements. Now I would say this is basically crystal structure or structure prediction. And we start with this empty canvas, and at each step, our action is to add an atom and place it somewhere on this canvas, and then over time we molecule until the bag is empty. And in the meantime, we collect rewards for placing these things correctly. And so you can see it actually works reasonably. It's admittedly very toyish examples, and you can see at different time steps how the structures look like, and at the end they're reasonable. And we extended this to a bunch of other stuff, but obviously around that time diffusion models came around and no one looked back. So then another thing I haven't talked about, but it's obviously very popular these days, is LLM-based generation. So it's actually really simple. So all you do is you encode the structures as strings. So there are different ways to do that. We talked about molecules. For materials, you could just use, say, a CIF representation, and then you're trying to generate valid CIF files. And then you just tokenize, and obviously it's a little bit tricky to tokenize these floats that tell you the Wyckoff positions, and I don't think that's really a solved problem. And then all you do really is prediction. And so here we have an example where they do this, so they get the string representation. They then prompt essentially a pre-trained llama model that they fine-tune, and here they used LoRa, so it's a sort of low-rank approximation, yeah, you're not doing full fine-tuning, but only on a small subset of the weights. And once you fine-tune, you kind of things. I think it works okay, but yeah, I'm not sure that SIF generation is really the right application, but obviously powerful, and I think they play a big role in generative modeling these days. Another thing that just came out maybe 2 weeks is this paper from Matter, where they try to jointly generate molecules and materials, which I thought was quite interesting. So here the idea is to start with the autoencoder, and so you basically try to get a latent representation that works for both and materials. Once you have this latent representation, you can then do diffusion in latent space, which is obviously very popular for images. And so you do the same thing. You start with random Gaussian noise, and then you're trying to denoise it. And trick they need to apply here is they actually need to add this class label to tell you whether it's a periodic or a non-periodic structure. And yeah, so they do this diffusion in a latent space, so then they get a sample latent representation. They use their decoder that they trained here, and then they can decode molecules or materials. Okay, with that, I want to thank all my colleagues and contributors, and thank you so far for the first part. Yeah, exactly.
So any questions?
Thanks, Robert. Super nice. I just have a bit of a technical question. When you do the conditional generation, so you've got the score that you add on, right, to your unconditional score. Do you have to worry about these? Do you have to somehow balance the the magnitude of these, or because typically the advantage of the score is that you don't have to normalize these in any way, but then now, so do you have to balance them somehow?
And just Robert, when you need to be closer to mic. When you answer, just be closer to mic, okay? No, just put your mouth closer.
For the talk. I was wondering how you're doing in terms of novelty of prototypes. So I mean, depending how you define it, you probably have in your training data maybe 20, 30 types already. And how how's the novelty of the prototypes you generate?
In general, also. Oh. Hello. Sorry. Okay, let me repeat. We didn't really look at that because defining prototypes in itself is a bit. We just looked at uniqueness and novelty. But obviously, defining novelty is also very tricky, I think, as we all know these days. So, the short answer is we haven't looked at prototypes.
Any other question?
Thanks for the talk. I was wondering as well, why you guys decided to only keep like really stable materials in the training data set. Like, would it not be useful as well to have some non-stable and then, I guess, conditioned towards stable materials, for example?
Yeah, that's a good question. So, I mean, first of all, we have this threshold of 0.1 of the convex hull, right? That's already quite a bit looser. You could argue maybe you should define stable as below 0. So that, but we'll exclude others. So notably, we won't have diamond in our training data, right? Because I think 0.14 EV above the hull or something like that. And so, yeah, could in principle include more structures and then condition on energy later. I think we did do this in some of the experiments. We found it helps a bit. It wasn't really worth the additional effort. I'm not exactly sure why, but yeah, it's definitely something to explore.
Thank you.
Okay, great. I don't know if there is other question or we can move. Jonathan, you would like? Okay.
I was always wondering in terms of generative models, I mean, let's say until the ternary space, I mean, I would argue that maybe we can exhaustively scan it even for stable crystal structures. And afterwards, I mean, quaternary problems then with disorder. What's your opinion on this? Are you also considering problem of disorder somewhere in the process?
So, if I understand the question correctly, was the first question, can you just exhaust the ternary space? Do you even need a generative model?
Yeah.
Yeah, I think the ternary space you can probably still exhaust. Once you go to quaternary or quinary, it probably gets a little bit more. And I think we also have some results for this in the paper.
So the question was that in quaternary it becomes disorder becomes a problem. So the question was, do you consider disorder also?
Oh, I see. Okay, yeah. So here we don't consider disorder for generation. We actually consider it for evaluation. Again, I will talk about this a bit in the tutorial. But yeah, ideally, you would have a model that knows about disorder, so you don't generate all these orders of essentially the same structure. But really, it's a very hard problem, and you need to sort of solve it on the model side, but also on the evaluation side. Yeah.
Okay, great. I think for other questions, you can catch Robert during the coffee break, and we can move to the tutorial while Robert prepares. You have a message to Slack how to download and install things for this tutorial. So if you didn't already start this, you can do it.
Thank you.
Yeah, let's thank Robert also.
Okay, let's. Okay. All right, maybe let's take like a 1 or 2 minute break. If anyone wants to go quickly to the toilet. right. Let's slowly get started again. Are we still missing anyone? Yeah, some people. Okay. So yeah, please open the tutorial, and then we can slowly. So essentially in this tutorial, I want to talk a little bit about how you can make some trade-offs between speed and accuracy, and how you can steer the generation process. We already touched on some of this. And I also want to talk a little bit more about evaluation, because it's really very tricky. So here we are essentially going to use the open source code. So suppose you want to sample stable structures that satisfy a particular space group, 225. And so the reason I chose this example is because it's easy to verify. Okay, in practice you can obviously condition properties, but then once you generate the structures, you also need to verify the structures. So you should either would have to run DFT, or you need to train like a predictor. And we haven't open sourced the property predictor, so it was a little bit tricky. Okay, so so what we are doing here is we are loading a conditional checkpoint, and maybe while I'm talking, you can already sort of execute the first two cells, the generation part. That might take some time. So yeah, we're loading a conditional model checkpoint base group from Hugging Face, and then use it for sampling. And as I mentioned in the talk, we pre-trained the model on a large number of stable structures, and added on a labeled set of structures that have space group labels. And actually, in this case, it's each structure had been labeled because space group is easy to compute, but it doesn't have to be the case. Okay, and then so let's look a little bit at the code here. So as I said, the model name is. So one thing we'll do to speed up the sampling is we reduce the number of denoising steps for sampling. So the default is 1,000. That's going to be too slow for us. So we're just going to reduce it to 100. And obviously the trade-off here is that the generation quality will be a little bit lower, but always speed. And so to do that, we need to override some configs for both the 3PM and another config. And we can also sort of explicitly disable generating some unsupported elements. It means is that one of the filtering steps we did for the training data is we excluded certain elements, for example, radioactive ones, because we don't really care about those. So in principle, the model should have no reason to generate those at sampling time because it hasn't really seen them, but it does sometimes happen, and so to avoid that, we can them. Okay, so so hopefully we can get the checkpoint from Hugging Face, and then we want to do conditional sampling using classifier free guidance. So in this fine-tuning step, we trained the sort of a conditional model, so we can do both the unconditional and the conditional score. Gamma controls the guidance strength, and so if we set gamma to 0, we're basically back to unconditional generation because score vanishes. And then increasing it further, so now we can talk a little bit more about the trade-off. Yeah, we will produce samples that adhere more property values, but usually what you lose the most is actually diversity, because our unconditional score has seen all these different structures, so very diverse structures. But for the conditional score, it might have only seen a few examples of a specific space group or whatever condition. So you have much examples and you will lose a lot of diversity. So now to sample, we will generate this, we will instantiate this object called a crystal generator, which gets the checkpoint information, batch size, and here typically the batch size we would want to say set as high as possible given our GPU constraints. In this case, we keep it quite moderate because it can be quite costly. And then we tell it what we want to condition on. So in this case, we condition on space group 225. In our case, we use a guidance factor of 2, which is still larger than 1, but not super high. So we find that to be a reasonable trade-off. You could, in principle, record intermediate denoising steps, which can be useful for debugging, but we're not going to do that here. And again, you can pass some overrides to the sampling config. And in this case, we're just going to decrease the number of time steps. And then once you have this generator, you can generate structures. You can save them to some output directory. And so it also prints the model config. So it seems it's still running. I don't know. I've actually prepared some sampled structures because I was thinking this might take a while. So I'm thinking maybe we just stop this. Can I just interrupt? No. Yeah. Oh, okay. No. Okay. Okay, so if anyone has already managed to sample, that's great. If not, in any case, we will load some pre-generated structures. So if it's still running, maybe for now also just terminate the kernel. Click here at the top, interrupt it, and then we just rerun. Is this just running a cell? We skip this one and go to the next one. Oh, yeah, okay. Where's the cell? Oh, here. Okay. No. I don't see the cell. What? How? Okay, great. Okay, now we're back. So let's just use these pre-sampled structures. And so the next thing what we usually do is we will relax the generated structures because obviously most, even though we are trying to generate stable structures, not all of them will be sort of at the ground state or close to the ground state, but a lot of the properties usually define with respect to that. So in practice, we do relaxation. Ideally, you do DFT relaxation, but here we can just use a force field. And even if you run DFT, we usually do pre-relaxation with a force field as well, because then you're still probably closer to the relaxed state, so the DFT should be faster. So what this is doing is it's essentially loading MatterSim, which is also a machine learning force field from our team. And so in this case, we have these 256 structures that we loaded. And now we're going to relax them. So that will take some time. So while it's still relaxing, I can already talk a little bit about the evaluation because I skipped over that earlier. So what we actually really want is to generate synthesizable structures, right? But that's obviously at this point pretty much impossible to predict. We also want them to be diverse, novel, and satisfy our target constraints. But even so, yeah, as I said, predicting synthesizability obviously is very hard. The best we can do at this point is basically predict thermodynamic stability at 0 Kelvin as a proxy, and we do that through the energy above the convex hull. And diversity is also very hard to evaluate, so we're just using uniqueness as a proxy. And another thing we do for stability, because we are essentially, most of the energies that we use during training were computed with PBE-GGA, we use energy correction from materials project, and I will correct for some sort of weird behavior for anions. And then uniqueness is defined as a structure is unique if it's different from all others in the batch that we sampled, according to structure matcher from PyMagen, and a structure is novel if it's different from all other structures in our reference data set, according to the structure matcher from PyMagen. And then we have this, and then we'll go to the property constraints later. Okay, and one thing we talked about is obviously disorder effects, right? So it's actually really hard to say whether a structure is different from another one. It's almost a philosophical discussion. And one problem is disorder, right? So you might generate one ordered approximation of a structure, one ordered approximation that's, or one structure that's actually an ordered approximation of a disordered structure, and probably you would consider them to be the same thing. Or at least you wouldn't claim your structure to be novel if you already know a lot of other ordered approximations. So what we are doing is we actually developed a disordered structure matcher that will take disorder into account. And the way we do it is we basically try out for certain elements if we can substitute them with other elements, and if we have any of those structures in our reference data. Okay, so, wow, okay, so relaxation is still going. So let's just keep going. So while this is still running, I'll just keep going through the code and we will catch up later. So once you have sort of relaxed your structures, right, you will, so next we want to compute the properties because we want to also evaluate whether our structures satisfy the properties. And then we will go through this evaluation. And so we have this matrix evaluator class, which takes our relaxed structures, their energies, their properties. Then we need a reference data set. In this case, by default, we use this LXMP data set that contains about 1 million structures. We use the stability threshold of 0.1 that I mentioned, this energy correction scheme, our disordered structure matcher, and the property constraint for space group. So here, this tuple basically tells you the range of values that you're happy with. So for discrete, it will just be the same value. But obviously, for continuous values, you might set this to a range. Or if you want something to be larger than something, then you just set the maximum to none. And so all of that works. And okay, let's go back. Okay, it is still running. Huh? Yeah, I don't know. Yeah, usually it should be fast. Yeah, it's already 6. So. Oh. No. Okay. I can also, I can just take the Sorry about that. It seems to be a bit slow. Okay. Oh. Okay. While we're still waiting, are there maybe any questions? Yeah. No, I don't think we are explicitly looking at oxidation states. Yeah, for sure. I mean, as I said, like how you define novelty is very hard, right? Ideally, I think ideally a material would be novel if its properties are different, right? Like even if maybe structurally it's very similar, if the properties are very different from what we've seen, then we should consider it novel. But that would be very hard to generally apply. I think that's essentially a shortcoming of doing high throughput. I think if you're sort of a computational or experimental material scientist who can look at the structures one by one, I think it's much easier to make that analysis. But I think in terms of high throughput, we really don't have a good way to measure that. Okay, I think this is still too slow. So again, if it worked for you, keep it. I will go for a workaround. And if it still stuck for you, you can follow me. So what I'm doing is I will just say I will just set the relaxed structures to structures at this point and get rid of this. And let's just say some of them will be stable. Right, let's try this. Let's just say they are all stable for the sake of running it. Great. Okay, so one thing I would, so let's assume we've relaxed the structures. One thing I like to look at is some sort of marginal statistics. So here we, for example, see the number of distinct elements that we generated in the structures, which I think looks sort of reasonable. Mostly we generate some ternary structures. And then we can also look at the distribution of elements. So this is now obviously is a conditional distribution, right? So this is most of the structures will have space group 2 to 5. So I'm not a material science expert, but I actually think this looks somewhat reasonable. I think some of these structures like to be in space group 2 to 5. Then we can actually compute their space groups. And so one thing to point out here is that and that's important, that we actually use a slightly looser threshold for the space group analyzer. So we use Preg 0.1 and angle tolerance of 5. I think the defaults are a little bit tighter. So if you use those, you might get a lot of P1. But if you use those, you get pretty reasonable distribution. So these are the top 5. So you see most of them are indeed have the right space group. Some of them are still P1, and you have some others. These are just the top 5. So then you can instantiate the evaluator. And you can compute stability, uniqueness, novelty, and so on. Obviously, because I hacked the stability now, because I didn't actually run the relaxation, they will all be stable. But that should be fine. And then hopefully we can still look at some metrics. So one thing that's nice about this metrics evaluator is that it uses a lot of caching. So we have a lot of metrics that involve stability or involve computing some form of uniqueness and so on. So we try to do it only once. So if we then compute composite metrics, we don't have to rerun those. Okay, so we're actually computing energies. Now we have uniqueness and novelty. And these 247 or 249, that's because it's usually grouped by chemical system or reduced formula. So we still have 256 structures at this point. Okay, so now we can actually look at the results. So stability is obviously usually not 100%. I would expect it to be somewhere around 60 to 70% maybe. And the other values should be fine though. So uniqueness still quite high. Novelty is around 58%. And if you then all put them together, it's still at around 58%. It should be a little bit lower usually, of course. and then about half of them satisfy the property, and if you combine them, around 14% are stable, unique, novel according to our definition and satisfy the property. And as I said, we do a lot of caching, so now we compute all the metrics we have, and it actually was very fast, so we can quickly look at them. So we can see the average RMSD from relegation. Well, that should actually be 0 because I set them to be the same, but yeah, so we can ignore that. We can look at average composition validity, structure composition validity, structure validity. So these are things like SMAC checker and so on. We can look at the fraction of novel structures. So we see that actually, yeah, okay, these are the structures, and fraction of novel systems. We see the diversity of chemical systems is actually quite a bit lower than a number of structures. So that is maybe a hint that diversity is a little bit lower. We also have precision and recall with respect to the reference data set, and yeah, also something like fraction of unique chemical systems. So in general, it will be hard to sort of optimize all of those. There are a lot of trade-offs. So for example, there's a trade-off between stability and adhering to the condition. There's a trade-off between stability and novelty. So for example, if we'd actually run for 1,000 time steps instead of 100, usually the structures will be more stable, they will have higher quality, but actually novelty will drop because you're better at just fitting the data at that point. So that's a very common trade-off. And yeah, obviously we talked about the guidance factor as another way to trade these things off. And so hopefully maybe when you're at home and have a little bit more time, then you can play around with this. Yeah, Metagen is open source. You can also train your own models, you can fine tune them and so on. And so hopefully this gave you a little bit of a small insight into how it works. And that's it. Thank you. And I will still be around for questions later as well.
Great, thank you very much. So yeah, if there is any question now, or you can catch Robert during the coffee. Okay, let's then whoever wants to catch Robert during the break. Thank you very much again. A quick reminder, if somebody from COS didn't sign the list for today, please do it now because I'm going to scan it. Does anyone know who is Bartosz Majewski? He didn't sign. Okay, maybe, yeah. Just I wanted to scan them now because the lady is going to leave, so okay.
Okay, we'll be starting the last lecture now. So, and say something about large language models and applications in chemistry. So, I hope you enjoy.
I'm gonna do some small tests here to see how far I have to take this from my mouth. Is this okay? Okay, I'm gonna try to keep it like that. So thank you everybody for being here and for the invitation to the organizers. So I'm Andres Brand, I'm a PhD student at PFL in Switzerland, and I'm gonna be talking about applications of large language models in chemistry. And the title is as general as it can be, because, well, you'll see a lot of things with this. So I hope you like it. Let's talk about large language models. I'm going to stop saying large language models because it's very long, and then I'm just going to say LLMs, right? So LLMs are just probability distribution over a sequence of tokens, over a space of tokens, coupled with a decoding mechanism, right? So if you like equations, look at this equation. This is basically, this is basically computing the probability of a given token under whatever probability distribution, and this probability distribution is going to be what the LLM learns. And the decoding mechanism is what happens whenever you talk to it or whenever you make it generate something. The probability distribution in itself is not necessarily very useful. You need to generate something with it, and this is why the decoding mechanism is there. So yeah, just keep this in mind. This is probably going to be useful in the future. But yeah, I'm just going to give a little example here of how decoding with LLMs work. So yeah, so let's say you have as a start in this token the, right? And so in LLMs you have this thing called the vocabulary, which is basically just, you know, the set of words that you have access to, right? So after the word the, you have possibilities of what you could say after, right? And so out of all of this, the one that makes the most sense is cat, right? And so we have a probability function that basically tells us how likely it is that this word or that this token follows, right? And so in this case, because the is an article, cat is a substantive, then you know, it grammatically makes more sense to have the cat than, for instance, to have the, right? That makes no sense, and so the probability distribution learns that, and yeah, this is all it's learning. So it's autoregressive in the sense that we're basically a sample from this probability distribution. Let's say we select the word cat, then we put that as an input again, and we decode again, right? So now we have the cat, and then we'll choose a next word, right? So let's say in this case, the cat is. And we continue with this process like that. Okay, this is actually messing up with me. Okay, there you go. Sorry for a spoiler, I'm gonna be here. Yeah, okay, so continuing with the decoding mechanism. So now we have this. And so at this point you have many options, right? You have the cat is cat, which is, I guess, true, but like not very useful. You can also say the cat is blue, the cat is black, or the green. And all of them are grammatically correct, right? But the LLM is not only learning grammar, but it's also learning things about the world, right? Just keep in mind that this is on massive data sets, and by reading so much, they learn a lot about the world, right? So like, even though it's grammatically correct to say that the cat is green, that's actually kind of odd. Like, you don't never see it, so you would never say that, and thus it's very unlikely. So the correct answer here would be kind of that the cat is black, and with that, you continue the coding and you finish. So now you have a sentence, right? This is how generates text. Everybody follow that? Everybody likes cats? Cool. So just as a summary of that, LLMs are basically this next token prediction. They're very good at that. They have been trained on huge amounts of data. I don't know how to explain how much data this is. Like, basically everything that is posted has been used to train these kind of models. So nobody could ever read so much except these machines. And the fact that they know so much about the world, as I showed with the cat example, makes them feel claims, right? And so, you know, if they know so much about cats, can they know, for instance, something about chemistry, right? This is a question that we can ask ourselves. And, you know, in some scenarios, useful. They don't have to be experts in chemistry to be useful for chemistry as well. So we're gonna see how that looks. I guess everybody here has interacted at some point with an LLM. And I guess I did a spoiler, but here you have it, right? Usually the way people interact with LLMs is through an interface like this, like ChatGPT, right? And so here, I don't know if you can see well from the back, but basically to draw a snake in ASCII-Arc, and it did, which is pretty cool. I mean, you can use this as a design. It's like pretty smiley and nice. So this is useful. I mean, I don't know, for my purposes, but you can ask them so many things, and I know that you have found them very useful for other tasks. Another thing you can use them for is to ask them, hey, ChatGPT, can you solve my homework? If you're a professor, this is a bit problematic. If you're a student, you're happy about it. But yeah. One question we can ask now in chemistry is, can LLMs check my homework, right? For solving your homework, you need to know some things. You need to be able to execute. You need to know like the basic concepts in order to solve that homework. And you know, they're doing this kind of research, like can they actually solve school level stuff? One question that I find more interesting, and at least in my lab we're doing more, can we leverage LLMs to solve or like to help scientists solve their homework, right? And this is more like, can we make tools that help them make, I don't know, new applications? Can we just generally make better predictive models, for instance? So this is what we're going to focus on today. And let's see how that goes. So there's many things or many ways you could tackle this question, right? And one of them is, for instance, data extraction. You know, there's a lot of data in the literature, right? Let me just do something here. Yeah, there's a lot of data in the literature. So it's a lot of things. They just publish really a lot of data, but everybody chooses their own format as they like it. Sometimes the data is in figures, sometimes it's in tables, sometimes it's in a PDF, which makes no sense, DFT people, by the way. But you can also try to solve hard problems with this, right? And whatever that means, we're gonna see what it means in my. You can try to build agentic systems, and I'm gonna be a bit deep on this after, but just keep in mind that these are just systems that interact with an environment and that can dynamically make decisions to solve a given task. And you can think about novel tools or user interfaces or user experiences. So before ChatGPT, you couldn't, I don't know if anybody was really thinking about something that you can talk to that will solve your problems, right? This is a novel interface and it happens to be very useful. But this is not the only way with these things or interacting with data. So if we give new ways to scientists to interact with data, this might actually be very useful. Let's say this is here. So how to work with LLMs? What does it mean to work with LLMs here? So if we go back to this equation, these tokens, as I explained before, could come from the LLM, right? So through the decoding mechanism, but you could potentially just put them as well yourself, right? They could be a process that generates tokens, and they come into the LLM, and then the LLM generates tokens conditioned on that sequence. I'm going to show you what that means with examples, of course. And of course, there are going to be silly examples in this slide, cat-related. So let's say one of the first things we could do is, let's say we give more, right? So we are in a world where cats can photosynthesize. I saw a cat. The cat is, you would expect that the cat is green, right? This makes more sense because I have more context in there. So this is a pattern known as in context learning. You're basically inputting more data as context for the LLM to pick from there. So the LLM has these kind of extrapolation capabilities that make it able to pick from the context and use that to generate an answer, which happens to be really useful. Let's say this other example here. Instead of this, just this looks like I'm talking to myself, right? I'm just describing something. This is just like normal text. But I can also have this kind of pattern, user and an assistant, right? So user says, my cat fell into a paint bucket with hex code this. What color is my cat? And the assistant will say the cat is, again, here For those who don't know, this is a green color, right? And so the cat is green would also be likely here. But then this is slightly different because now, I mean, in an interaction between two, this is more like role playing. And this is all text generation. Like, I don't really have to have 2 separate systems or 3 separate systems. Basically, the LLM can just assume that an assistant is giving an answer to an user, right? Because it's put in this role, right? And this is the way that we do it. This is another way of conditioning the generation of the LLMs and called instruction tuning. And this is the usual way that you interact with systems like ChatGPT. You don't talk to ChatGPT like this. It would be kind of cumbersome to say, hey, let's imagine, no, or like you solve your homework with ChatGPT if it was like this. Yeah, I don't know. You would put the question and then the answer is, and then it would just continue generating, right? That would be kind of weird. And so like with it is this. And there's a last pattern. I mean, there's a lot of patterns that you can use here, but like this is another one that I like. So, and that we're gonna talk about a lot here. And is, let's say you have this. So answer the questions using the tools provided. The tool list is gonna be get color and search Google, and then question, what color is my cat? And now, people just give an answer and say, I will use a tool because it was instructed to do so, it's in the context, right? It makes sense. And then it will say, the tool is get color. So now at this top generation, we can take this answer and we can execute it externally. So let's say that's a Python function or something like that. We take it, we execute it, get a response. So let's say, you know, because I created this tool, the tool tells you that it's green, right? Why not? And now this is kind of like on the fly generating internally to put in the LLM. So in this case, of course, the LLM will say the answer is, well, green. The cat is green. And this is a pattern called, right? This is going to be very useful for agentic systems because LLMs, yeah, they know a lot. They might know a lot because of the huge amount of training data they have, but they don't know everything. And even if they know everything, they cannot really operate in an environment, right? If you want a robot to, an AI like ChatGPT or something, to be able to, it will not just do it like this, right? It can generate the email, but it will not send it because it cannot really interact with the outside world. And so this is a way of making LLMs be able to do things in the real world, right? We just give them access to external tools. So yeah, I hope all of them were clear. Sorry for the silly examples, but convince you that cats can be green. So now let's finally talk chemistry. Let's say, again, an agent, as I explained before, can be defined like that or with some pattern like that and a set of tools, right? So what we did in this work was designing a set of expert-curated tools and systems operate with a task, right? So this system will be just something that takes a task, which in this case can be something very general, and explained in natural language, something like plan and execute the synthesis of length. And with the given tools, it will try to solve that task, whatever that means. So what we do with ChemCrow is the following. It takes those and it takes that task, and what it will do is, okay, reason about it, like what do I need to do to solve this? And make a plan, right? So, okay, you know, the first thing that you have to what you want to make, right? The next, so this is what it does, right? So it selects a tool to help it go forward with this task. The next thing is, well, as I explained before, you take this and you run it externally. And this gives you some sort of observation. It gives you an output, right? And then you put this output back into the system and let it think again. Right? And this goes in a cycle until the task is completed. So, okay, the tools that we use. So back then we, used GPT-4 because it was really good. Here tools, much anything, right? You guys have been talking about a lot of tools during the summer school, and I wish at some point you can integrate this with an agent. That would be amazing. But yeah, let's say back 10 years ago, we used some molecular tools, like, tools to calculate molecular properties, to get convert names, databases, and so on. There's reaction tools, and so we have this, which is, it helps you plan how to make a synthesis, but then also a robot, right, which can execute the synthesis. And then you have other tools that can be used. So you have access to Python, you have access to a search engine, and finally, you know, safety tools, because chemistry can be dangerous. So why not? Can you see this? Okay, so I'm gonna read it out loud anyway. So yeah, let's say for this task, what's gonna happen is the following. So in this planning stage, what the LLM will do is, okay, given all of that, it's just generating tests, right? So it will say, I need to know which insect repellent to synthesize, right? That makes total sense, so open. So I will do a literature search to find a common insect repellent. And so what it does is select a tool, in this case, a literature search tool, which is basically papers and getting information from them. And it will say common insect repellent, right? Now, we execute the tool externally, and we get back the picaridin of different insect repellents that you have. And then we go back to the beginning of the loop, right? So now that it has this information, it says, I will choose DEET as the insect repellent. But first I need to get the smiles of DEET, right? So now it will select a different tool that basically will be executed externally. This tool is named to smiles with DEET. And so it will just come back with the smiles, right? So this is the smile strings for DEET, and we just give it to the model because it requested it. So the pattern that you see here is that it's dealing with an environment defined by tools, and it's just, you know, deciding what to do to go forward with the task. So now we got us miles of a molecule that it wants to make. Right thing. I mean, for now it's just a database, but you can consider one of the tools that you have for molecule generation, right? For conditional material generation or something like that, right? That would not be a problem. And so, okay, now that I have the synthesis, I will plan the synthesis. The molecule, I'll have the synthesis, so you use the reaction planner for that. It gets you recipe, how to make it. And finally, okay, now that I have a synthesis plan, the last thing to do, of course, is, well, now I'll execute the synthesis. So you use the reaction execute tool with the input. This will go and launch a full synthesis on the RoboRxN facility in IBM Zurich. 2 hours later, you get this nice message saying that the synthesis procedure was completed. If you go to it, there's a little liquid air with DEET. And yeah, so we can claim with this that we just did the first LLM-driven AI, LLM-driven synthesis, which is pretty. So this system is literally operating on an environment, and this environment is the real world, and so it can actually make things, which is really nice, right? Like, this is giving a lot of more power to tools, right? Now, you might wonder, but Andres, this is so easy. I mean, I could have just come up with this workflow. The point is that sometimes things happen. You cannot just plan everything in advance. You need systems that can decide as they go, right? So here comes the problem of decision making in chemistry, right? So let's say you want to run this reaction, and you run it, why not, right? You get something like this. Can you see that? If you cannot see that, it's just like a lot of things. What is in there? Is it only the product? Or do you have a trace of this? Or do you have some of the, some of the catalyst that was used, some of, all these things, reactions. So you need to think about doing workup, doing separation, doing, washes, doing a lot of things, and then how to separate. Do you just like one, or do you need to do a column for that as well? So there's a lot of decision making involved in this. And yeah, I mean, I cannot just list how many things you have to think about. Chemists are very good at that, but make a specific workflow for this, you're gonna have a hard time. And so that's why we need systems that are flexible enough to take decisions on the fly. This was work that we did with a lot of people. Now, so yeah, going to the problem now of doing novel tools or user experiences and sort of like solving hard problems. Now to retrosynthesis again, because I happen to like it. Problem of retrosynthesis is the following. You have a molecule that you want to make for some reason, because your model told you so, because your chemist promising, I don't know, for whatever reason you had a molecule. And now what you want to do is basically find a set of reactants. So let's say this one, such that when there is a reaction available, that will convert this into that, right? And now you have a potentially simpler molecule. With this, you will just do the same, right? Find some set of reactants that upon reaction under certain conditions, they will give you this, right? And so now you have two molecules that are simpler, but now you have to repeat this over and over until you get things that you can buy, right? Like this. The way this is solved computationally usually is through Monte Carlo tree search. And this basically works just by, like you start from the target product, you apply a bunch of reactions that you have in a library, and then through some rollout process, you like a score that indicates how promising that specific expansion is, and then you decide to expand on that, and then you iterate again, right? So this plus you how you grow the tree, or like how you explore the retrosynthesis as you go. The current state of this is that you get something like this. This is like so the yellow thing is the final product, the one that you want to make. And then you have just like a bunch of routes that you have as options. And now you as a chemist have to go through them, select them. And like any of them, well, that's on you. So this is, what did I do? Oh, I can do that. Okay. So this takes away a bit of flexibility. Really tell it what to do. You just like, look, here's my molecule, do something. And as a chemist, you want to have control. You cannot really put constraints, and what if you want to work ideas, right? If you look at the molecule, you, at least as a chemist, you might say, okay, I want to make it like this because, I don't know, I feel like that. But with these kind of systems, you cannot, right? And they're expensive. So observation that, coming back to LLMs again, an observation with LLMs is that they're quite good at analyzing chemical reactions. So given that you have a chemical reaction plan, you can give that as context to the model, and it will ask it to analyze it, right? And it will generally be very good at that. Something like this is just like a bug protection here of this primary amine. You can ask it to analyze it, right? So it will tell you, something like this. Okay, this is a protection reaction. It's to an amine. Or you can ask it to explain you the mechanism of this reaction, right? So this is a nucleophilic attack of the primary amine on the bulk anhydride, right? So forth, right? There's many possible things that you can do with it, and this is pretty good. Like the current models work very well for that. So how do we leverage those capabilities? Just get a nice text explaining you something, but how do we actually do something with that? Let's say what we can do is just integrate the LLM inside of the search, right? And let it guide, right? So if you remember, we have here like this rollout phase where we basically pick a new position and evaluate how good it is, or like how much potential it has. We can complement that with an LLM that can basically analyze the reaction so far and tell you, okay, this makes no sense, or this makes sense, and go better this way, and continue exploring like that. Of this is that you can add more information to the LLM to guide the search towards things that you prefer, right? So for instance, it will not just the ability of a given reaction, but it might also tell you, but it might also like be able to evaluate the alignment to a prompt, right? I'm gonna show you what this means. Or it can also consider experimental conditions. I cannot use palladium in my reaction, so don't give me anything with that, right? The LLM might be good at that. And yeah, so what does this look like? You have a molecule like this that you want to synthesize. Okay, I want you to break the pyrimidine in the early stage, but get all other rings for commercially available materials. If this doesn't tell you anything, this is basically like break the molecule here early. Touch any of these rings here. Like, don't break them. I don't want you to break them, right? How do you do this? Like, how do you get only routes that apply only like this, that align with this prompt, right? The way that I showed you before, that's the way, and I'm gonna show you that it works. You can have different strategies. So for instance, use a convergence strategy that joins two fragments of roughly equal complexity near the end of the route. This might be another strategy that a chemist might think of. And this is similar. You have to break it roughly around here somehow, like in this area. but late stage, right? Which means you're gonna build up blocks, and then in the last 2 or 3 reactions, you're together. The previous one was you form that ring early on when the molecules are still very small, and then you build around it, right? There are different strategies, and so if you have a specific strategy, you're gonna struggle with current systems. So there's where we come. So yeah, let's say basically what we're doing here is just, I just explained what we did, right? It's, given this query, like break this, and don't break this. So like, don't break this ring, and break this ring, right? This, a synthesis that looks selected, right? Which is nice. But a synthesis that looks like this, where this ring was not broken, even though it was asked for it, would get a low score, and this is pretty much what we want, right? So they all to chemists on what they can do, right? This is just building a new retrosynthesis tool where the chemist can decide where to go with this, how to synthesize things. Benchmark for this, right? And I can go in depth more about what this means, but basically, this works. And yeah, so we made. It's very laggy, and probably you can see much, so I'm just gonna skip it, but I hope you got the general idea, right? So there's a huge, well, not huge, we're 5, but yeah, it was pretty cool. And with that, I think I am on time, so I have 2 minutes. You wanna talk? Anybody who has questions?
So any question?
Yes, thank you for the talk. I was thinking that there is a problem with materials, that some are not synthesizable, no? And can you combine these to the search for materials?
Yeah, this is something you can consider doing. I don't know that much about materials. I mean, to some extent, but and I haven't explored how good they are at telling you how synthesizable something is. But I guess you can try, right? Then you will encounter issues such as representation, right? Basically, you want to encode everything as text, and so for instance, for molecules, it's kind of easy because you have. But with materials, I guess you can go with like ZIP files or something like this, but they would need to have some understanding of 3D structure through ZIP files, which I think is more that people has shown that they can actually generate this. So there's no reason why they wouldn't be able to assess the synthesizability of something. Now the other thing is more a general ML problem. Like, I don't know if there's out there a lot of ZIP structures of things that are explicitly non-synthesizable. So pretty much every set might just be synthesizable, right? So I'm not sure how that would work, but yeah, maybe. Like, why not? You can try something like this.
Thank you very much for interesting talk. Could you tell me a little bit more about the task you showed in the middle of the presentation when you had the robot who is doing the synthesis? So I was wondering about the risk assessment and certainty of taking actions, because when you do synthesis, some of the actions might lead to failure or something might just go wrong. So how do you implement this risk assessment during taking action, during synthesis?
Hello. Yeah. So yeah, let's go back to that slide. That's a great question. And I'm not gonna give a simple answer. Sorry about that. Yeah. So in this, so there's basically 2 answers, right? The first one is on the side of the agent, right? We can implement some sorts like safety measures to make sure that nothing wrong happens, right? So the LLM is instructed or trained or whatever, like is conditioned to only execute something if it has already run some safety screenings before it, right? So like, let's say if you want to make a molecule that is explosive, that is known to be explosive or very similar to an explosive molecule, it will check that, and if it is, it will just stop executing. It will tell you, okay, you're not making this, right? So that's one way of tackling it. And the other way is, well, they're just not out in the free, right? You can constrain what they do through the communication layer, right? So if they send instructions that can be detected as dangerous or that can be just filtered out by, for instance, explosiveness of or toxicity of the materials that are used, then this is simply not done. And then the other answer is from the side of the robot itself or from the lab itself. And yeah, I mean, generally, if you're running a safe lab, then you don't have explosive things in there if you have an automated platform, right? Like you're basically trusting that the automated platform will not explode, and you make sure of that by just not having nitroglycerin as a reagent, right? And also just like from the layer side, you simply screen again. So we cannot just do everything, and it will not just break because there's safety measures implemented at a lot of stages of the process. But it's a great question. I mean, it's necessary when you're thinking about self-driving labs. Like you need to make sure that the pipeline is not going to break. Thank you.
Thank you. Any other question? I don't see any, so I guess you can go to the tutorial or take a minute if you need.
I guess I can use this one. Probably. Hello. Ah, why? That's weird. Okay. Ah. Why it's on?
This is just for short answer. This is still remain.
So do we just start with the tutorial, or do we take like 30 minutes rest or 30 seconds rest, or what? How do we go from there? Okay.
I sent it on Slack.
Ah, great.
You can notify people that it's on Slack.
Okay. That makes sense. So yeah, something that I didn't really talk about, but you might be aware of, is that these models are huge. By huge, I mean like, I think you were talking about like 100 million parameters models, and that was very big. These models are 600 billion parameters or so, right? So that's what we call LLMs. You have smaller models, but then we call those like small LLMs, and they're still like 3 billion parameters. So this is pretty big, right? Which means, although we can run them locally, we're just not gonna, because that is an issue in itself and it's outside of the point of this tutorial. So we're using this, we're using OpenAI. This is a service provider. They're basically just like, we're gonna learn here how to make requests, how to talk to an LLM over an API. And for that, you're gonna need that API key. So make sure that you have this in your first square, in your first cell. Thanks. Yeah, let's make sure you have that, and yeah, just execute it. If you, for some reason, have any issues with this, let me know as soon as you have it, because it might just be rate limited, which means I've never really had 60 people run this at the same time. So if any issue, I will just give it another one. But yeah, so let me know. So yeah,
Okay. So yeah, if you have an issue, you have to select the kernel T10, but it's alphabetical, so it's on the top of the list. So it's T1, then T10, then T2. So make sure you select the correct one.
Yeah, I saw that was happening. So anybody having issues right now? If not, that means everything's going great. This is going to be an easy tutorial, right? We're not going to have to wait a long time for things. We're not going to have to install anything. This is pretty much being handled from the side of OpenAI, right? So like all the computation is happening somewhere else. So you don't have to worry about this. So let's say the first thing that we're going to do is making a simple request, right? So how do we communicate with an LLM that is running somewhere else? Usually you have an API. An API is just basically just like some service that they provide. Can you see this? Can you see my screen? Even the ones in the back? All good? Okay. Cool. So yeah, this usually looks like an URL, right? This is the endpoint where we're communicating to, right? And then, yeah, you have some, I don't know, some extra information. So for instance, here is where you pass the authorization, which is your API key that I just provided. And then here's some data that you have to send, right? So if you need an answer, you might as well just give it an input, right? So in this case, we're inputting, say hi to all the students in Zadar, right? And the model that we're going to use is GPT-4o Mini. That's just a name. And this is the way that we're going to communicate to it, right? So we run that, and we'll see what comes back. So you have all these, huge JSON file. Not huge, but, it's a big JSON file that contains a lot of information that we don't care about. We just care about the text here, right? So hi to all the students in Zadar, right? So yeah, this is basically the LLM responding to my request. And yeah, we can just print this out, right? So, it's like responding with emojis and everything, very ChatGPT-like, right? So this is kind of a, very easy example, but this shows you in a very low, in a low level, how we communicate with LLMs. Every time we communicate in the future with LLMs, we're not going to be doing this. But this is just for you to know how it works in a lower level. What we're going to be using now is LangChain, which is a framework that basically handles all of this for you, right? So imagine you had to write this every time you want to communicate with an LLM, right? You just, I don't know, you don't. So you use LangChain or any other framework that handles this for you and that gives you a higher level of abstraction to operate with LLMs, right? So this is something you install, and then, yeah, it should be installed, I guess, in the environment already. So we just run this, and now, look, now basically we import this function, init chat model, right? Because, OpenAI, GPT-4o Mini is a chat model. And now we can initialize the LLM as an object in Python, right? So this is the way to do it. And now we can just invoke the LLM, right? So instead of writing all that JSON, we're just gonna, create a human message, and this is gonna be the input, right? So let's say this is a more chemistry-related question. I'm gonna ask it, what functional groups are present in this molecule? Let's just look at this molecule. I think I forgot to put it in. Yeah, this is the molecule that we're talking about. Right, so what functional groups are in this molecule? Do you see it? Right, so, the AI will just give me an answer, after I execute it. right? So this would be the answer, right? It has some content, and this is a long response about what functional groups are in that molecule. Did everybody follow up to here? Like, no issues so far? All good? Dobro. So yeah, this is the answer, right? Now, what do we do with this answer? Like, it's not very useful. You can read it, you might learn something from it, but how do we use this to do something else? Like, what does it do for me? So yeah, this is not very helpful. So what we're gonna do is try to leverage all these prompting patterns that I showed before. So for instance, in context learning or instruction following or stuff like this, to create prompt templates, right? And so let's say okay, a prompt template can be defined like this. You just have, a template is basically something that has a given shape. So for instance, something like this. Well, functional groups are present in this molecule, and then just like a placeholder, right? So now I can just run the same thing for multiple molecules if I want, or for different molecules. I don't have to stick to this. Of course, that would be pretty useless. But now I can change the molecule as well, right? And I just tell it, okay, the input variables are gonna be as miles, right? So now I can execute it like this, right? I define as miles first, and well, now I visualize it. And finally, I can just simply get the prompt template, and now that I have a prompt template, you can connect that with the LLM itself, right? So the prompt template in itself is not doing anything. This is simply like putting pieces together, like helping you craft a prompt to be able to leverage one of those patterns that I spoke about before. But now you need to connect this with a language model, right? So this is what the concept of chains come in. And this is why this library is called LangChain, because you're basically chaining language. That's the whole idea, right? So now you can create a chain that basically has this prompt and uses this LLM, right? And so this is very specifically done for that prompt, right? And so the next thing I need to do is just, okay, we take that chain and we invoke it with these smiles. I don't have to be writing a prompt over and over. I could just replace the smiles, and I'm gonna get, this answer like this, right? So here's the molecule, and the answer will be generated here, right? If I wanna change the molecule, I just define another molecule and I execute it on that molecule, right? I don't have to be typing in the prompt every time, as you would do with ChatGPT, right? So this is becoming a bit more useful, right? If I wanted to do it for several molecules, I just have, let's say I have a database of molecules, and I just iterate over all the molecules, or I just apply this function to all the molecules, and I would get responses for all the molecules, which is slightly more useful. Now, let's talk about in context learning. As I said, this text in itself is not very useful. You can read it, and it's probably correct to some extent, but it's computationally not very useful because it's just text. What do you do with it? One thing you can do is now try to incorporate formatting, right? So it might be more useful if I get a structured response. So instead of all this text, I get a list of functional groups, and maybe I can do something with that, right? So here we can use in context learning, right? So now basically I'm doing the same. I'm just gonna build a prompt template that takes as miles as an input, but then the template is going to be a bit more complex, right? So now I'm going to tell you, okay, you're an expert chemist, and your task is to identify the functional groups of the given molecules. Give the name of the smiles, give the name and the smiles of each functional groups, and then, let's say in context learning here means that I'm basically giving it examples of molecules and how I want the response to look like. So let's say for this molecule, this is an example that I'm giving directly in the prompt, right? So this molecule, and then the output will be 1 point space, halogen, bromine, in parentheses, right? 2 point, pyridine, and then the smiles of that in parentheses, right? 3 point space, cyclohexane, and then the smiles of that. How is this useful? This will basically condition the probability distribution to make it generate whatever it has to generate in this format, which is more useful because I can probably then parse that response and get things that I can use somewhere else for something else, right? And so this is just giving examples of how I want things to look like to condition the probability distribution, right? And so here I will just do like input, smiles, and then output, what will it be? Well, it will be something that looks like this format, but now that is applied for this molecule. I hope that makes sense, but I mean, I'm anyways gonna give you, examples. So let's say, yeah, we have these molecules here, right? I'm just gonna iterate over all of them and run this. So let's say for this molecule, now instead of a bunch of text, I'm getting output and then all the functional groups with smiles in a good format, in a format that I can use to parse this, to extract the functional groups, to do something with them later, right? So it's not just free text as it was doing before, but now it's actually, something that looks a bit more structured, which is very nice. Like, it's nice to be able to just guide the LLMs into doing something more specific. And this is very nice because I don't even have to fine-tune the models. I don't have to train them for anything. I'm just conditioning the probability distribution on the tokens that come before, right? So just giving them different contexts, right? So now you see the same thing just being repeated. Let's say for this molecule, you get something like this, which is more correct, right? And so on and so forth, right? So, yeah, I hope that was clear. Let me know, if anybody is lost, if anybody is getting issues with the API key. No one? Great. So let's move on into the next application. I talked about, just as comment, data extraction in the presentation, but I didn't really get into it, right? So this is one of the huge applications of LLMs, right? They basically serve as generic translators, right? So they can translate you between English and French, or between, I don't know, whatever language, but they can also take information and turn it into a different format. And this format can be something that can be more useful. So let's say I give it a paper and I get, I don't know, I get the title of the paper. Let's say that's an easy one. Or I get a class. What is this paper about? How can I classify this paper, right? Something like that. One that was very interesting for me, at least, is extracting data from an organic synthesis, right? So I'm going to show you how this looks like. Basically, you have to define a model, basically what kind of format you want the output to look like. So for an organic synthesis, you want many things that you want from it, right? So for instance, you have a product, you have reactant, and let's say you have temperature, right? These are few things. You have many more, but let's say I'm only interested in this one. So basically in this data structure, you have to define what is the type of each of the fields that you want. So in this case, a product is simply a string, right? And then I'm just okay, I describe it. So the main product of the reaction, right, that's the product. In the case of the reactants, it might be more than one, right? So it's not only a string, but it's a list of strings, right? And then I just describe it. The reactants used in this, right? This is just me telling to the LLM what I want from it. And then the temperature, well, they not always report a temperature, but if they do, so it's optional, but if they do, it has to be an integer, right? Because I want. And so the temperature in degrees Celsius, right? This is the requirements that we have. And then again, we just make a little chain like this, where we have the LLM, but now we're gonna use it with structure output. And the structure output looks like this. I'll show with an example what that means, but this is basically how you write it. Once you get used to the syntax, it's actually quite easy. You do this all the time. And let's say we have a procedure like this, right? If you read an organic synthesis paper, you will see that they do something like this. So they state the product, they state the number of the product in whatever nomenclature that they want inside of the paper, and then they tell you, okay, a single necked 500 milliliters round bottom flask was equipped with a whatever. Read all of this and tell me what is the temperature, right? But I can just do it with the LLM, right? I don't need to wait until some of you respond. So look, the product is just, so this is the synthesis, the extracted synthesis as I want it from the LLM, right? So let's say you have basically here a product, which is a string, and this string is this one, right? Then you have reactants, and that is a list, and this is the list of reactants, right? And then finally you have the temperature. Now the good thing about this is like I can directly just get those individual things from this object. So let's say synthesis product is just gonna be this. And now I have it, and now I can use it. I can do things with it, right? And this is quite useful. Or let's say I want to do something with the temperature, right? So now you have synthesis.temperature, and you simply get it, and now the temperature is minus 78 degrees Celsius, right? Because we asked it in degrees Celsius. We can check if it's correct, but you know, I pretty much trust it is here, like minus 78 degrees Celsius. What else are the reactants, right? You have these isopulegol, you have, what else? Methoxy, you have methanol, and what was the other one? Ozone. There's ozone somewhere. Right, so it's taking me time to do this. The LLM just did it like this. And this can be very useful. This is very scalable. And look, like this is something that you can actually use in whatever context. So let's say you're doing Bayesian optimization and you're doing it in the context of, I don't know, you want to like take things from the literature to inspire your BO algorithm or like let's say to initialize your search space, right? You get a lot of papers. What do you do with that? You convert that into something that you can actually use, and you know this is a very useful way of doing it. Everybody follows so far? Do you think this is useful? Nice. So yeah, last application, agents, and of course I had to put some agents. So I'm just gonna be very basic on this. Like we're not doing ChemCrow again, right? But I'm just gonna show you how to plug in different tools, how to plug in different things, right, into these agents and how to operate with them. You can read one, but let's go into the thing. So some tools come directly pre-made for us. We don't have to rebuild tools every time. And so, for instance, from LangChain, you can import this Wikipedia wrapper, right? So this is basically some tool that when you run it, it will just do a Wikipedia search and give you the answer, right? So I just like search atorvastatin, which is it's a drug molecule, which is very cool. And so like that, this is the answer from Wikipedia, right? Now, we cannot really do anything with that directly. What we're gonna do is put this tool and give the LLM access to this tool so that it can search things in Wikipedia as it likes it. So yeah, this is how we define a tool set. Basically, we just like write a tool, we give it a name, we take what the function is, and then we describe it. So this tool is useful to get accurate information from Wikipedia. And now finally, we just defined an agent with whatever name that you want. We initialize the agent with the tool set, with the LLM that is going to power the generation. This is just the type of agent that's more like a technicality for now. Let's not worry about it. And verbose just means that it's going to tell us each step of what it's doing. Right? So you just initialize it. And now if you run it, let's say what we want to do here is, again, what are the functional groups of these smiles? Right? So if we run it, what it's going to do is the following. It's going to start generating step-by-step things. And so it will first think a little bit about what it has to do. It will select an action, and in this case, the action is just Wikipedia search, and then it will give an input for it. So functional groups in organic chemistry, right? This is a very general query that it decided to do, and so it will, like externally, now we're gonna take that, or like the whole framework is just doing this, like taking that as an input, taking this tool and giving it this input, right? And executing it. And now when we get a response, we put it back into the model, right? So we use all of these as context for the model. So this is basically just like, the page about functional groups, right? The next thing it will do is, okay, now I will think again, right? So to find the functional groups in this command, I need to break down its structure. So it's just doing a little bit more thinking. So it did another Wikipedia search. So it searched for acyl chloride functional group, and so on, and then it will just finally tell you an answer. Why not? So this is probably not the most useful tool for this task. Like, you can definitely think about better tools for doing this than Wikipedia, right? So one thing we can do is just, if you have interacted with RDKit, it allows you to create or to extract the functional groups of a molecule very easily. And so we can just add this to the set of tools in our agent, right? And create the agent again. So now we have two tools. We have functional groups tool and we have the Wikipedia tool, right? So if we execute this with the same prompt, now we might get something different because now we're telling the model that it has access to another tool, right? So in this case, again, same thing. It's thinking about what it has to do. It decides that it's going to use the functional groups tool, and it will use this as an input directly. The tool tells it the molecule contains ketones and halogens, which is quite fair. Look at the molecule, right? Why not? And now with this observation, it has enough information to tell us that, yeah, the final answer is this, right? It contains ketones and halogens. Sorry. So you see, this is a very high level way of doing this. Like, I told you about these prompting patterns before, but I'm not really doing any of that. The framework is doing all of that, right? So let's look at what the framework is actually doing, right? So yeah, this is kind of, let's look at the prompt template of the agent, right? Can you all see this thing, or should I zoom in more? Okay. So yeah, let's say the prompt template here, or whatever we're giving to the language model as context, is basically this whole text. So we're saying, answer the following questions as best as you can. You have access to the following tools. So you have Wikipedia search, takes a string, returns a string, and it's useful to get accurate information from Wikipedia, functional groups, and so on. And then use the following format, right? So here we're doing tool usage, we're using following instruction, we're doing some, in context learning to some extent, right? And all of this is to bias the probability distribution into doing things the way we like them. These models are so good that they actually manage to do this in a nice way. So basically, this is what's happening behind the curtains. Again, you don't have to write this every time. The framework just does it for you. This is what's happening behind the curtains. And so, yeah, like with that, we can, try to do a more useful agent now. So let's say we have this other tool, which is the same one that I use for DEET, right? Like the model used this to convert DEET into the smiles, right? So this can just like be a database lookup, let's say in PubChem, something like that. You wrap it into a tool. This is in the utils directory, and you can add this into your tool set, right? So now we're again gonna initialize the agent this tool, and we're gonna run it. So now this is gonna be a bit more complex task, right? We're gonna do the following. We're gonna try to, find the functional groups of caffeine, p-bromobenzaldehyde, and cycloserine, and then find what they have in common and find some information about it in Wikipedia. Now, if someone wants to try to do this as I run this, be my guest, and we can make a competition. That's going to be fun, but I can just run it here, and then you'll see the output. So this is not a complex task itself, but it takes time. I mean, you basically have to look up 3 different molecules. You have to do the same operation for them, and then you have to try to match, similarities, and then you have to go ahead and find information about it somewhere. And this is a toy task, but you can think about more complex workflows. So the one that I showed before, right? This example where you have this reaction, you have to make a lot of decisions on the fly. That can be one case, and you don't need to specify a fixed workflow for every possible task. You just give tools, have a powerful enough LLM, and then you basically try to, you can specify what you want in natural language such that it will just try to solve that task. And so if we execute this, this is what we're gonna see, right? So, first I need to get the smiles of each of the molecules. So this is what it's doing, look. It's getting the smiles of caffeine, it's getting the smiles of p-bromobenzaldehyde, it's getting the smiles of cycloserine. And then, now let's get the functional groups of all of things, right? So it's getting now the functional groups of these smiles. So it has ketones, the functional groups of this one, and of this one. And then, now it's doing some analysis here, saying, it concludes in the end that, all three compounds have ketones, and these two all contain halogens, right? That's one of the things that they have in common. And yeah, finally, we'll just like do a Wikipedia search to give a final answer and tell us something about the ketones, right? So yeah. I don't know, ketones play an essential role in biology and industry with examples including sugars and steroids, right? Like, why not? So, and this is the final answer, right? So quite easily, you already get your answer. This is fairly complex task. And the key idea here is that you don't have to make a specific pipeline for this. This is just giving a bunch of tools to a language model, and the LLM can use them directly to solve tasks, right? So this is what we mean talk about agents. Now you can start thinking about how this plays out in a framework like ChemCrow that I showed before, right? You basically give appropriate tools for it to do the things you might possibly want to do, right? And so if you want to ever execute something in a lab, well, you better give it access to a lab. Like you better give it access to a tool that connects to a lab, right? Something like this. Or if you want to be able to do, I don't know, molecular generation, then you better give it access to MatterGen or, you know, some other thing, right? So yeah, I think we are, do we have any questions? Yes. Thanks.
Thank you very much. It's not related to the tutorial, but a general question regarding do you somehow prevent hallucination of the model before applying it to some complex task? For example, is chemistry information less prone to hallucination because of the structure of the text or something? How do you deal with that?
That's a great question. So there's ways of dealing with that, right? And one way of directly dealing with it is by using these sort of structure outputs, right? So if you go back to the example on data extraction, one way of preventing the model hallucinating is constraining the generation to only these fields in this particular data structure. So if it does something that deviates from it, we will get an error, and it will try to repeat again until it does it correctly, or until it just decides that, okay, I cannot do this, so I just break down, right? So this is one way of handling that. And you know, this works to some extent, right? Like, what if it doesn't have a product in here? Well, you know, it might just make something up, right? And so the other, let's say, way of doing this is, well, you can do it like downstream, right? So for instance, one way of dealing with that is like, once you have this thing, you can use validators inside of this, in this data class, right, of this base model. So there's these functions basically that check that everything makes sense. And so one way of checking that things make sense is, for instance, well, if you're telling me that you found a product, but when I try to find that product in the context I gave you, I don't find the string, then that's kind of sketchy, right? This works to some extent, again, but yeah, basically the answer here is like giving context, doing kind of this constraint generation, and then doing validation after in some way. Depends on the problem. Yeah, okay, for this one in particular, we have a paper on that. I didn't really put any on this about it, but yeah, we can see. There is some, so if you check out this paper, there's some measurements here. I mean, the whole paper is basically about, okay, how do we extract these things? How do we put them together? How do we build a benchmark for this? And then finally, how do we evaluate? And this is a very relevant question, because like a big part of it is how do we like define a metric for this? What is success? Like at the level of synthetic routes, success is not only did you get this one product correctly, but did you get the whole graph correctly? Or how approximate is the graph that you extracted from a ground truth? And so I guess there's like different levels of evaluation that you can do here, but we decided to do on the graph itself, on like the synthesis tree. And back then we found very variable results, right? It depends on how you measure, it depends of course on the model, it depends on the specific implementation. But yeah, you can more or less trust them. And I mean, when you do these kind of things, it depends also how you parse the data, right? So if you have PDFs, what do you do with them? Like, you need to convert them somehow into text, or let's say images, but there's, you know, there's a big question here on how do we send the text, or like how do we extract it to be able to give it to a language model? So yeah, this is kind of like a little plot showing all these different variations and how they play out. But yeah, I mean, it's basically context dependent, right?
Any other questions? Maybe. No?
So did you get like to the end of the notebook? No API errors. Okay, I'm proud of that. That's great. Cool. I guess I'm the one you from going to the beach. So so I guess if no more questions.
Questions? Let's thank Andres again. Okay, I guess we came to the end. So for some of you it's a segment, for some of you it's a happy moment. For me it's mixed feelings, but I'm happy that it's done, and I'm happy that everything went really smoothly. So as always, I would like to give a lot of thanks to different people. So actually I would like to really start with thanking all of you. I think you're really a great group of people. There was really absolutely no problem with any of you. So from this perspective, I had a really easy job. So thank you everything. I really like that I saw you also somehow socialized well. You have different, dinners, drinks, and things like that. So I think it's a nice community also in growing, starting. So yeah, that was really great. Then I would like to really thank a lot our lecturers and speakers for really nicely prepared lectures and tutorials. I think we really saw a very nice overview of the field from Nicola that gave us also some industrial perspective and also his previous perspective of how modern materials modeling works. Then Ilyes, who really showed us state-of-the-art machine potentials. Then Jonathan, that had to leave a bit early, but he showed us how all the high throughput data generation things work. Tristan, that also had to leave, show us the coarse graining. Martin is still here. No, he also left. Okay, but we saw other ways how to how to model some other properties except the machine learning potentials. And then maybe we had other section with, and then Johannes for the excited states. Are you, Johannes, still here? I don't, you're here. Thanks a lot. And then we had, I think, people that had more connection with experts. So we had Milica, who showed us how to do Bayesian models. We had Lucas, who is, I know, you are still here. Great. So for compressing models, and then who did I miss? And then I think that's it. And then today we have generative models from Robert, thanks, and then for the last LLMs from Andres. So I think really we covered nicely the field, and I really hope that you at least have now a feeling what's going on, and especially those that are just starting, that will be able to find something interesting for them and go for it. So thanks, lecturers, again. I would like to again thank all the sponsors that really make all this possible. I heard that it was nice, all the things we provided, but it wouldn't be possible without them. So basically Demon that provided most of the funding for all the lecturers to come here, and also some of the other things. University of Zadar that gave us this for free and organized all the food and things like this. Psyche, and that provided some financial contribution. CCAM also financial contribution, plus all the web page and all the things. Max also provided some financial contribution. Croatian Science Foundation through my project. And then big thanks also to Srce that supported all the tutorials on their resources, and my institute that provided some funding. So I really thank them all. Then I would also like to thank a lot my colleagues. Kevin unfortunately had to leave, but Federico, Katarina, and Jure, I think you all saw that Jure did a great job with all the computational stuff. So let's thank you maybe. Katarina, I think, did a great job with managing all the participants and sending all the emails and everything. So I think, and Federico really helped a lot to get all these fundings. So let's thank him also. And then there are, of course, some next steps. So if you want to remind yourself what's happening here, recordings are available on this channel on YouTube. We will eventually try to also split them nicely according to the lectures and things like this, and hopefully upload it to Lumos that Federico mentioned. It's probably going to take some time, but you have the whole days currently on the YouTube. Srce, guys, it's enough to extend everything for 1 week. So if you want to play around for the next week, all the Jupyter servers will be still on, so you can break more if you didn't have enough time for something. Well, if you like what's happening in our cost action, you can join via this link. We'll have another schools and events in the next years also, so you might follow that. I also sent on, no I didn't, but I will send now a link survey, so if there is any suggestion how we could improve, please write us. And I guess that's it. I really enjoyed it. Have a safe travel home. Unfortunately, we don't provide now lunch, so but I see you were been quite capable in finding places. So there will be, at least for some of you, some time to still hang out. Have a safe travel home, and hope to see you soon. Thank you. That's it.